December 2025. PJM Interconnection, the largest power grid operator in the United States, runs its capacity auction for the 2027-2028 delivery year. For the first time in the organization's history, the auction comes up short 6,623 megawatts below the reliability target. The shortfall is not an accounting artifact. It is the gap between what the grid promised and what it has. And the gap is widening. In Texas, the ERCOT large load interconnection queue swells past 233 gigawatts, nearly 3 times the entire state's current peak demand, while only 23 gigawatts of new generation actually synchronize. The era of passive grid management is over. The grid is now a dynamical system governed by Kirchhoff's laws and the swing equation. Generic AI wrappers and standard predictive models cannot meet it where it lives. The reasons incumbents fail are structural. A single transient stability simulation across PJM solved by traditional differential algebraic equation methods takes hours, so real-time contingency analysis is impossible. Static line ratings on transmission corridors are calculated under worst-case temperature and wind assumptions, leaving 20 to 40% of a line's true thermal capacity unused. The interconnection queue is clogged with phantom loads, speculative hyperscaler applications across multiple sites, hedging on whichever utility wires up first. And the replacement math is brutal. Replacing 1 megawatt of retiring thermal generation requires roughly 5.2 megawatts of solar or 14 megawatts of onshore wind to maintain equivalent reliability. Veriprajna's answer is not an AI wrapper. It is a physics-aware engine built in 4 interlocking layers. The first layer is physics-informed neural networks, or PIN. Unlike standard neural networks that learn only from data, PIN embeds the laws of the system directly into its loss function. For generator K, the network is trained to minimize the residual of the swing equation. M sub k times delta double dot plus d sub k times delta dot plus the network sum of voltage terms times the sine of the rotor angle difference minus the mechanical power input. By using automatic differentiation to compute the velocity and acceleration of the rotor angle, the PIN determines system states up to 87 times faster than conventional numerical solvers and at any specific time t without sequential time stepping. Look ahead during a potential blackout becomes near instantaneous. The second layer treats the grid as what it actually is, a graph. Substations are nodes, transmission lines are edges. A graph attention network learns which neighbors matter. Alpha sub ij equals the softmax of leaky ReLU over the sum of leaky ReLU across I's neighborhood. When a critical substation fails, the kind of failure that put 1,200 megawatts of Baltimore load at risk, the GNN predicts the propagation of voltage dip and frequency oscillation across the entire topology in milliseconds. The third layer is dynamic line rating, fed by LiDAR conductor monitoring. The fourth is an agentic control layer, where reinforcement learning agents make dispatch decisions inside a constrained Markov decision process, with voltage and frequency limits as hard physical constraints. The benchmarks are sourced in concrete. AES deployed dynamic line rating across transmission corridors in Indiana and Ohio. Transfer capacity on 345 kilovolt lines rose 61%, on 69 kilovolt lines 25%. The AI and IoT project cost $0.39 million, against an estimated $1.63 million for traditional reconductoring, a 76% cost reduction, deployed in 3 to 6 months instead of 2 to 3 years. For predictive maintenance, a multilayer graph neural network achieves an F1 score of 0.8935 for identifying substations at risk of failure within 30 days. Stacked LSTM models predict coal plant retirement ages with a mean absolute percentage error of 1.072%. The effective load carrying capability for demand response rose from 69% in the prior auction to 92% in the latest, driven by a regulatory shift requiring availability for every hour of the year. The opportunity is clear. Intelligent agents that can guarantee that 92% without disrupting industrial operations. The board-level argument is 3 lines. Capital efficiency, GNNS and PIN identify true stable operating limits, deferring billions in transmission and generation investment. Orchestrate the assets you have instead of building new steel. Interconnection acceleration, agentic AI screens the 233 gigawatt ERCOT queue, separating credible projects from phantom load. FERC Order 2023 mandates cluster studies. Automating those studies turns years of human engineering hours into months. Risk mitigation. The NRDC projects $163 billion in cumulative capacity costs across PJM states from 2028 through 2033. The 6,623 megawatt gap is not a deficit. It is a mandate. We build the deep mathematical and physical engines that make the grid sentient. PIN for stability, GNNS for topology, reinforcement learning for control. The grid is no longer a collection of wires, it is a graph of intelligence.